That's fair. It's starting to slow down people joining. I'll keep admitting everyone, but yeah, I reckon we can get started now. So hello, everyone. Welcome to part 2 of the SUMO speaker series. This week we have Accenture here with us. We have Nicholas and Oscar from Accenture, and they're here to tell us about big data and machine learning. And so you guys know how it goes. If you have questions, feel free to interrupt with your mic, unmute yourself at any time, or send it through the chat and I'll ask them, or you can wait till the end if you want to. But besides that, yeah, I think we're ready to get going. Okay.
Awesome. Thanks,
also,
Josh.
Sorry, one more thing. I'll just let everyone in here know we are recording. So if you feel uncomfortable with cameras or anything in that sense, then just keep that in mind. But yeah, I think we're ready to get going besides that.
Awesome. Thanks, Josh, for the intro. Good afternoon, all. It's so great to see so many of you here. We're up to almost 100, which is really awesome to see. So thanks for coming today. My name's Oscar, and I'm joined by my colleague Nick. And yeah, as Josh said, we'll be talking to you today about big data, machine learning, and a little bit of cloud as well. Just before we start, big thanks to SUMO for the invitation to be here today. There's a lot of aspects of uni that I don't miss, but you know, any mention of SUMO, Tron Lab, PNR, you know, brings a tear to my eye. So thanks for that. We hope we can, you know, inspire a software-oriented mechatronics career for you guys. For those of you who have nightmares about control registers or pointers or the like. So let's get started. Oh, sorry, where are we? Yeah, so what we're going to run through today, just a little bit about us, where we come from and why we do what we do. Nick's going to run through a demo with some big data and cloud engineering. And then I'll run through a machine learning demo. And so hopefully there's a lot there to unpack and, you know, as I say, a lot to learn, plenty of questions we hope from you guys. So yeah, please do interrupt us. And we'll try to reserve at least 15 minutes right at the end for any questions and answers that you guys have. So if there's something general, just save it for then. But yeah, otherwise feel free to interrupt. Cool. So a little bit about Accenture. We're one of the world's biggest technology companies that you've probably never heard of before. We've got more than 550,000 employees across 50 countries. So just to put that in perspective, we're one of the top 10 government companies by employee headcount in the world, on the scale of about FedEx. So we're pretty big. And what we do is we're a technology consultancy that helps you know, other big companies manage their technology so they can focus on their core business. So just as an example, let's take a big Australian bank, for example. They've got lots of data, lots of computing resources and services, and you know, servers. And if any one of these go down or have an issue, you know, that might affect their core business or their customers. And that's obviously a negative outcome. Now, solving these problems in-house is, of course, possible, and a lot of companies, you know, have teams that can do this themselves. But it can be hard and expensive to, you know, find the right skill sets and stand up a big enough team to manage this. So, as a consultancy, we've been helping companies do this for almost 70 years now. So, by bringing Accenture in, you know, to your business, we can potentially lower your cost for monitoring these services and fixing things. And, you know, by scaling that out across many businesses, you know, we can realize big savings across, you know, the whole industry. So part of how we lower costs for our clients is by automating things that have traditionally required humans to do. And so that's where we come in as software engineers, building the automation that can, you know, help fix these problems to lower costs. So just a little bit about us, just so you feel comfortable asking questions as we go. I'm a dog person, but I have 2 cats at the moment, which has been a bit of a learning experience, but is nice all the same. And my favorite color is orange, obviously. Growing up, I always loved technology. And so that's why I did Tron. I didn't really know what part of technology I wanted to get into, but Tron seemed like, you know, a mixture of hardware, software, plus a bit of space engineering for good measure. I also studied finance on the side, but that was more of an interest rather than something I wanted to get into. But it definitely helped, you know, dealing with other business people. And I'm sure a lot of you are doing a BCom for the same reason. During my Tron degree, I was always the hardware guy. I was the one, you know, building the circuits and the electronics. And it was my mates or my teammates who were, you know, developing the software. So I didn't really see myself going into a career in software. But in 2019, in my last year of my engineering degree, I almost by accident ended up doing my ESIPS placement at Accenture. And, you know, the rest is history. So I did a thesis in computer vision, sorry. And I've been with the company now for a bit over 2 years since starting my SIPs. And I'm now running the machine learning team, which is super exciting. So that's everything you need to know about me. I'm going to pass over to Nick now to introduce himself.
Thanks, Oscar. Yeah, unfortunately, I didn't go to, as you can probably tell by my sort of blank expression, I didn't really go to USyd, so I didn't really get many of the jokes said, but I will say that, yeah, going to UNSW probably had a similar experience to Oscar in that I did mechatronics and biomed over there. And for me, I knew I liked maths and science, and it was, didn't exactly know what I wanted to do, but I knew that if I did that, as well as biomed, because robots and prosthetics seemed like the cool sort of thing to do back then, I figured I'd like something out of there. And yeah, did some society stuff regarding to like maker projects and also other sort of mechatronics projects during uni. So love that sort of stuff. And it was a good excuse to go to Queensland, I think, and stay up there for a couple of days for those projects. So that was also a big incentive for me. But yeah, I guess the more I went through uni, and I guess particularly with my thesis as well, was more sort of on the software side, and with uni subjects, and where I thought, you know, the software gig isn't half bad. And then, yeah, when I did the Accenture Tech Bootcamp, which was essentially a 4-day assessment center project style gig, that was something I thought was really interesting. And then, then kind of say the rest was history from there. So I've, yeah, kind of been a bit everywhere in the sense of started off doing some client stuff. But as we focus more towards building products, it's been more of the actual, I suppose, working on the technical side of things. And then now sort of migrating to be the product owner of this sort of monitoring platform that we have for our automation. So I still do some technical implementation, but not to the same extent as what I did probably a year ago. And yeah, aside from work-related stuff, massive fan of hiking and camping. So I'll definitely be out for at least a week once we can all go outside in the great outdoors. To keep the theme, I like red. I think blue is a bit overrated as a color, or too many people say it, so something different. And my token fun fact about myself is I once got lost in Wanglo State Forest. So not sure if that mean anything to anybody, but if you know where that is, you probably know it's not the best place to get lost. So that's all for me. Oh, cool. Me again. Yeah, so I guess, yeah, slides are a bit boring, so we'll try and buzz over this as quick as possible, and then we can always refer back to this if people have questions or are curious. But I suppose what we want to show off here in my little section is how, like an example of how we could do data analytics or apply it. So, you know, like with anything, it's involving the cloud, it's very freeform in the sense of there is no one correct way to do things. However, this is just one such approach. So currently, there's a lot of terms here and a lot of pictures, and people are probably going to wonder what exactly is going on here. Essentially what we want to build, but essentially what we're showing here is some sort of platform where multiple users can access the information they need and get use out of it, because ultimately this should be something that is useful at the end of the day. So yeah, to sort of run over it briefly, we have something called Kinesis Firehose, which is essentially a managed way to stream data into different sources. And we are going to stream this into 2 different locations. We're going to show that off in 2 different locations. We're going to stream it into AWS's Elasticsearch service, so it's a managed Elasticsearch cluster. And we're also going to stream it into a service called S3, which is essentially almost similar to Dropbox. You can almost think of it that way. And so Elasticsearch will, this currently emulates our current setup, which clients access our Elasticsearch and use our dashboards and visualizations to track the health of their apps and what's going on. And S3 is used for our internal business intelligence and data analytics teams to actually go through and look at information at the lower level. So to facilitate this, we use stuff called lake formation and glue, and this allows us to build what we call a data lake. So it allows us to essentially partition all of our data into separate stages. So we can have sort of semi-processed or unprocessed data initially set up, and then we can use glue, which is essentially ETL, so extract, transform, load pipeline, which lets us basically extract data from a database or a storage area, apply transforms to manipulate the data and add and modify fields, and then we can load it into another area. So we can process our data in stages, and that gives us a lot more control over what we can do with the data, and once we find out a suitable use for it. And then tools like Athena and Redshift are data analytics tools which we'll step through, and different people can use those tools to either do some exploratory searching of data or some, I suppose, what we call data warehousing, and I suppose lower level data analytics. So it's really designed for, I suppose, 3 different users, and this is something that is actually kind of relevant to us because we were kind of looking at options to do more thorough data analytics. So for context with us, currently we use Kinesis Firehose and the Elasticsearch service. So only those top 2 items. Everything else is still a work in progress. And I mean, we only really have started looking into the last 2 weeks. So apologies in advance, I can't answer all your questions because I didn't really know many of these services existed until 2 weeks ago. But like with anything here, it's, everyone's always learning this stuff, and it's, I guess, it's a work in progress on everyone's front. So I guess, with all of that out of the way, I guess we'll jump through each of these in a demo. I think, awesome. Thanks, Oscar. I just realized it's not like Teams where you can't boot somebody else out. Sweet. So I think we'll step through each component, and again, happy to take questions or go over individual parts if people are curious about it, either in here or towards the end. But what we have here is Kinesis Firehose, which is the first component where our streaming data is loaded. So for context right now, I've set this up locally in my own account such that we have data being streamed in from sort of these, I'm emulating here like a heart rate tracker. So we have a timestamp, a device name, which I've given dev or prod, and I'm generating a random float for the heart rate. And this random float's variable for each of the 2 different devices that we're emulating here. So we're sending this information to Kinesis Firehose, and we're telling it to basically manage the processing and the loading of that information. So you can think about if you were to design this yourself, maybe this example is very simple, but if you were to think about with what we do with hundreds of our assets all sending hundreds of logs and metrics per second, dealing with that and manually processing that yourself with your own managed software would be incredibly difficult. So having a tool like this is really handy, and being able to get metrics and monitoring on what is actually happening. So we can see on average there's about 8 put requests per second, which lines up with what we'd expect because we're sending about 10 records a second. So it allows us to see where this information is going, and we've configured it to send to 2 sources. So the first of which here is Elasticsearch, which we'll grab over here as an example. So with Elasticsearch, what we can do is we can actually go through and search for our data. So this, you can kind of think of it, would be the portal for our, for us, it's our client teams. But you can almost think of this as, in this scenario, it could be a portal for maybe like clinical trials or particular, maybe there's an app or something and you can track your own heart rate. So obviously, this is a very basic example, but in our actual Elasticsearch, we would have all sorts of different tenants, and we could make sure that only certain people can see their own data, and that obviously you're not able to see someone else's heart rate information or personally identifiable information. So we can take that data and we can construct visualizations to see exactly what's happening. And so we can take these data points and then we can aggregate them and view them. And then we can produce simple things like this. For our actual clients, would be showing them things like logs, things like resource usage. So if they're having any issues with their application's health, and also stuff like usage information. So we deal a lot with automation. So the key one is how many automations are we getting? And then how, in terms of configurations, how that's going on a time series. So very basically, you can see one is higher than the other on average. And that's to be expected because that's how I've hard coded it in this example here. So this is sort of one way for you can think our clients to look through this data. And you can think of this containing sort of important sort of time series data that's relevant for the short term, because again, you'll be checking recent activity using this for the other use cases. But another example we would want to use is sort of longer term tracking of information. So to do that, we're actually also send our data over to S3. So if we go to the configuration for our Kinesis Firehose component, we also tell it, in addition to putting this information to Elasticsearch, we also tell it to put information into S3. And you can kind of think of this as our durable storage, where we're keeping things for long-term usage. And it might not be as relevant for, let's say, clients or direct users, but for internal business intelligence and data analytics, it might be something that's more helpful. So as an example, this is what the objects actually look like. So you can see the way that Firehose manages the batching is that every minute around abouts, we have a new file written to S3. So again, it does that management for us. And again, it helps make things clean. So you can imagine if you could definitely do this yourself if you wanted to, but it would be a lot more difficult to manage that. So having that managed service makes life a lot easier in that sense. And so, what we can do then is using this S3 service as our sort of behind the scenes durable storage, we can configure this service called lake formation. And that will allow us to basically say, we can create what's called a data catalog, which basically allows us to define where our data is located and what the schema is. And so this kind of sits at a level on top of where S3 is. So you can think of S3, like I said, as being a low level storage. And this is a way to, I guess, achieve governance and say, define the schema, but also say only these resources or users can access these sections of data. So it allows you to have further control over that as well. So in this case, we simply define a heart rate database, and we say from this, make sure it's connected to this bucket that we've defined here. So in that way, if we were to change or modify this lake formation resource, the underlying data would still be there, which in that case means that we can recreate it then, and it means that from a disaster recovery perspective, that's a lot easier to manage. Within our database, we have tables, and we can actually create this table dynamically using what we call a crawler. So again, this is something that I'm not super familiar with, whether it's an AWS term or a generic term, but essentially a crawler crawls through the data and automatically generates a schema. So it's that idea of you're removing that manual work. So you're not only saving time there, but you're saving on people making errors, because people make typos, people can't spell like myself, for instance. So you're avoiding that, and you're making sure that, again, if you did have to recreate this, it would be a case of just crawling through the data and establishing the schema here. So as an example, we can go through and check the crawler, and it took about a minute to run last time I ran it, and it's a bit hard to see, but it basically automatically created this table. And through here, we can see that, we can confirm here through the data that the timestamp looks like an int, the device name looks like a string, and the heart rate looks like it should be a double or a float, and it's identified those things there for us. So of course, we could override this and say it should actually be this, but as long as the data is consistent coming through and of high enough quality, then you can do this here. So again, that's just another thing that we could use in the future to allow us to make sure that our schemas and tables are not defined manually, and that if we did need to recreate this, because things go wrong all the time, we have that there for us. So now that we have the databases and the tables defined, what we can actually do is now query that information using that. So there's two main ways in which we can query it here, and one of them is called Athena. So this allows us to run SQL-like queries, or actually exactly SQL queries, on data in S3. And that's quite powerful because we don't need to load the data elsewhere. We can simply run the queries as they are. And this is quite useful from like a data exploration point of view, because we can ask very simple things. Let's say we've got an unprocessed data, and let's say we want to check and see what the fields look like and how they're structured. We can easily do that through Athena before we implement some sort of ETL job, which will process the data in the way we see fit. So it's very good for ad hoc data, I guess, analysis and investigation in that sense. So in this case, I have a simple query here, which again uses the database and the table which we've defined from our crawler, so the automatically generated table that we've got from Glue. And you can see that each of these fields matches. And all we've said here is give us a unique count, you can kind of think of it that way, of the device names. And it's said that we've got 2. And again, that confirms what we think, because in my example, I've just hard coded dev and prod. So if we were to have more, we would see that change. But things like this are a good example of how we can define sort of very ad hoc things and just check, do things match with what we think? And if not, or if maybe fields aren't in a certain format that we like, then we can, like I say, add those ETL jobs to do that for us. And I think the other way we can do it is through Redshift. So there's a term called data warehousing, and essentially Redshift is a managed data warehouse. And so some people might wonder what that means. It allows us to do what we call analytics, data analytics and processing. So we can load up to petabytes of data and perform processing on these things. And so we can run these queries across, like I say, petabytes of data and get results and insights with the flexibility of using it in the cloud as well. So the awesome thing about this is that we can run the queries similar to Athena directly through S3. And so this means that we don't have to load data, we have the option of not having to load data into local storage to do the analytics on. And so from a setup perspective, that obviously makes life a lot easier in terms of you just have the data in one place. You don't have 2 copies of the data and then have to worry about if they're in sync. In many cases, again, there's always trade-offs. In many cases, it would mean that because you are loading from an external source and not internal local storage, things might be slower, for example. So there's always trade-offs of, do you care about cost or speed? But in this example, just to showcase it as a feature, we've configured it here to read from the same location. And because of that, if we run the queries, we can actually, in this example, just see how many documents exist currently. And you'll notice that it might take a few seconds. And again, because it's built around processing, entries rather than directly for speed, it will take a few seconds to run. But the idea is that this scales with size. So we've got about 6,000 here. And we can run some simple, averaging and standard deviation. Let's say we're doing statistical analysis and we're trying to see if the heart rate is statistically significant. Lazy me, unfortunately, couldn't be bothered to remember how to do stuff like t-tests. But again, just to showcase what it's like, we can do stuff like averaging and standard deviation. And again, this will scale for 6,000 or 6 million data points relatively effectively. And we can do this without loading stuff into local storage. And you can see these are returned in using SQL format. So there's no requirement to know any specific query language. And yeah, I suppose this means that it allows you to generate insights a lot quicker and to centralize all of your data through one source. So happy to take questions now or later, but I would like to give Oscar enough time to go through his stuff as well. So happy to wait a minute if anyone asks questions. Otherwise, also happy to answer them in chat if people want to post them there as well.
Yeah, cool. If anyone has any questions specific to that demo from Nick, feel free to call out.
Yeah, I've got a question. Oh, Steve's also got a question. So I was just wondering, Nick, in your job, are you mostly doing like data analytics, or are you like implementing like this software, like these new softwares like Redshift and stuff?
I would say most of my job is as a product owner, I guess, coming up with the vision of saying, okay, well, what would actually be helpful for us as a wider team? And I guess currently what we're looking at is in terms of analytics for and visualizations for client and engagement teams, there's quite a bit there, but we're not capturing enough data over the long term to answer sort of high level questions. So I guess coming at that vision and how we should achieve that is one part of it. In terms of the analytics, I would say that's something I do a part of, but it's not the main part of it. So I'd say,
yeah, okay.
Looking through the technology and how we can best apply it to what we want to do.
Awesome. Cheers.
Yeah, there's one more question in chat. Steve wants to know, at a high level, are the advantages of this infrastructure to be able to deal with those petabytes of data as opposed to a simple server running Postgres instance? A Postgres instance.
Oh, good question. Yeah, I think one of the big aims that Redshift has, and again, apologies because I don't have all of the facts in my head concretely, but the idea behind it is that you can run these queries extremely quickly across huge amounts of data. This is a simplified example for obvious reasons, but imagine that you are Accenture or some other large company with petabytes of data, and not only a large amount of existing data, but new data coming in every second. Being able to run those effectively and quickly is a big problem that a lot of, I guess, existing like legacy data warehouses struggle with. There's obviously a lot of low-level details in terms of how Redshift actually does that. So is actually able to accelerate those queries and run them effectively. But I suppose also other options include the pricing as well. So what we showed off here, you pay per query. So there's no actual cost for a cluster or for, you have to pay this much per month. It's you pay per query. And again, there's a trade-off there. If you run a lot of queries, it might be in your best interest to actually have a dedicated cluster or infrastructure and manage that, because that might save you costs, but it purely depends how you use it. But yeah, that different pricing model might appeal to customers who maybe run a few queries, but yeah, infrequently as well. There's a few things there.
Cool.
Sweet. I'll hand over to you, Oscar.
Cheers. So let me just put my screen again. I've got a very quick, again, a bit of just pre-reading. Could I get all of you just to drop in the chat how familiar with machine learning you all are? I guess I'm just wondering, like 0 for never used it, 1 for used it a little bit, and like 2 for I'm already an expert. Cool, a lot of zeros, which is perfect. So this will be very accessible because, when I started at Accenture, I had never used machine learning now. So yeah, super keen to teach you guys about it in what I'll call our crash course in machine learning for big data. So we'll start with an imaginary scenario. So similar to the monitoring stack that Nick just presented, imagine we have, we're constantly receiving data, and maybe it's monitoring, heart rate like Nick was. And almost always that data is okay. But sometimes it goes out of bounds. There's an error, there's a problem, something breaks. And at the moment, there's a human manually watching this data come in, 24/7. So we need a whole team of people to do this around the clock, checking each other's work. So we want to replace these people with a machine learning model, so that these people can, go and do something, more interesting, more useful with their time. But let's say in this scenario, we have a testing environment. So not only do we have the real, server that we're monitoring, for example, but we have a test one that we can, manually break and monitor. So how do we approach this? Well, one solution, one way of dealing with this would be to build a very simple supervised classification neural network. And we'll come to what that looks like in a second. But basically what we have is we have both, the real healthy data, if you like, and the, broken, problematic data. And what we'll do is we'll train the neural network on both the real data and both the healthy data and the false data or unhealthy data. And we'll train the model to, learn to distinguish between those two. So I'm going to call this our naive case. It's naive in the sense that we have both halves of the data equation. We have the healthy data and we have the unhealthy data. So what does a neural network actually look like? Because you've all probably heard the phrase. Neural networks are actually very simple, and the diagram might look scary, but it's really not. The input layers we can think of as just numeric inputs. So, in the case of, Nick's heart rate monitoring, that could just be a single number representing the heart rate, or it could be the past 5, heart rate samples, if you like, or in the case of this diagram, the past 3. Maybe we're interested in how the 3 relate to each other. What we do is we apply a series of mathematical functions to these numbers, and that's represented by the arrows. And so in the blue layer, we have what's called a hidden layer. So these are, again, just numbers. And this comes from the input layer. So in this case, it might be a summation of, the values that came through in the arrows. So maybe it's a, multiply sum type mathematical operation. And then finally, we could have any number of, hidden layers. We'll just work with one for now. Finally, we have the output layer, which is where we might have, our actual value of interest. So in this case, this will be a Boolean true or false, 1 or 0. And we'll train the model to output you know, a 1 or 0, depending on if that data is healthy or unhealthy. And so the training process feeds the input in at the same time as the output. And depending on, you know, what the output is computed by the network at the current time step, we just iterate through. So we know roughly what the output, you know, which direction the output needs to go in for each data sample. We can feed that back through the network and update, you know, the functions, if you like. At the end of the day, this is just a big mathematical expression. So I've probably butchered that, but that's the, you know, 5-minute how a neural network works. So let's do it. Let me actually show you how we program this. And by all means, feel free to follow along. Cool. Can you see my GitHub there? Cool. So feel free to follow along. The URL's there. And yeah, I'll just show you this very quick neural network before we go on to the more complex case. So we'll look at the data that I'm using for this demo firstly. So this is a freely available data set from online. And what it does is it describes banknotes. So I know cash is definitely in the past, but you know, fraudulent banknotes, forged banknotes were certainly a problem for you know, for authorities. So this is a data set that will you know, that contains both real and fraudulent banknotes. So what we have is we have 4 features or inputs, and these have been generated through some computer vision type transformation process, which I don't understand, but it's not relevant for our demo here. And we have a label. So this tells us whether the banknote is fraudulent, if you like. So at the top of the data set, we have a lot of a lot of legitimate banknotes, and they're just represented, as I say, by these 4 numbers. And if we go down the data set, at the bottom, there are some false ones as well. So they're labeled 1. And you can imagine that it would be quite difficult to build an algorithm, you know, just by inspection or, you know, similar methods to take, you know, these values and make a reasonable prediction as to whether they're real or not. So what I'll do, I'll just quickly show you the code because I think there's a perception that neural networks are scary and that machine learning is very difficult. But I like to spread the message that it really isn't. And, you know, starting from this code base, I'd hope that any of you that are interested would be able to, you know, get started building your own neural networks to experiment. So just very quickly running through the code, as I say, we load up that data set using these column names. So we've got the X's, which are the inputs, and the single Y output. We split the data set so into both training and testing sets. So we train the network with the training set and then evaluate it using the testing set so that we understand its performance on unseen data. And literally, that's pretty much all there is to this. We build a very simple model. So this is a sequential model. So as we know, there are 4 numeric inputs. I've defined a hidden layer here, which has 16 nodes in it. So there'll be 4 times 16 of those arrows, if you like, in that first step. And then there's a single output node. And what this sigmoid activation is, it basically just caps the output between 0 and 1. So that will give us, you know, the probability, if you like, that it belongs to the 0 class or the 1 class. If it's 0.5, you know, the model would be unsure. And what we do is we literally just feed through the training data that we made above, and then we can evaluate. And that's really all there is to, you know, your first machine learning model. So as I say, I definitely encourage you all to, you know, fork the repo, have a play around with it yourself. But I'll just run it for you now. Sorry, I can't actually see that behind the. So, so this model is built using the TensorFlow library, which probably a lot of you have heard of. It's certainly the one that we use. It's the most production ready machine learning library. Anyway, and that's all the time it took to train. We can see at the very beginning, on the first training epoch, it only got 50% accuracy, which is kind of what we would expect. The model when we first create it is only like flipping a coin. So it only gets it correct, 50% of the time. But by the very end, and you saw how long it took, it's only a couple of seconds. We've trained a model that can identify, fraudulent banknotes with 98% accuracy, which I think is really cool, that we can, a very simple model, and, come to this conclusion very quickly. What I want to really quickly go through, because we are running out of time, is a slightly more complicated model, which is really at the cutting edge of what research is currently looking at. And that is called, well, I'll give you the scenario to start off with. So say we take the, what we've just done, but we have a harder case now. We aren't able to, simulate the unhealthy data. Because, say it's a, say we're trying to detect hackers breaking into our system. We don't know what the, hackers look like. We can't simulate a hacker really. All we can do is, we know that everything's going on at the moment is approximately normal. How can we build a model, that can identify a potential intruder without really knowing what an intruder looks like? So the solution, or one possible solution, is building what's called a generative adversarial network, or GAN for short. And GANs have been, a really hot topic for the last couple of years. They were only invented about 5 or 6 years ago now. And they've been really talked about because of the ability they have to, generate new types of data. And I'll come to that in a second. The idea is we have a discriminator and a generator. So the generator actually takes noise and builds some kind of output that, eventually starts to look real. And we have a discriminator, which behaves just like the classifier we just saw, in that it, has to tell apart real data from the generator's output. And we actually train them side by side in competition, which is a really powerful technique. And, it can be a bit scary when you first, think about the implications of that we can actually have computers train themselves to do this kind of task. And, when I first heard about these, I thought they were really scary. Not just from like a, how do we build one perspective, but, from a, I guess an ethical perspective, training models to think like this. But, it's a really powerful technique. And, I think it's a force for good. It's the idea of a GAN, probably where some of you have seen it. The discriminator is given both real images. So in this case, pictures of people's faces. And the generator is just fed noise. And in a similar way to before, as the discriminator, the discriminator is tasked with telling the real images from the fake images. But as the generator gets better at that, we also train the generator to get better at tricking the discriminator. And so what we eventually build is a neural network that can, in this case, build a face from just noisy input. And so this is probably where you might have seen GANs in the field. There's some cool demos online of, converting artworks into photos using the generative power of this neural network. But what we're going to do in this case is use this generated data to actually train the discriminator to do the classification for us. So I probably don't have time to do this in a lot of detail. But what I'll do again, I'll just show you the code that does this and walk you through it. So again, we import the data, but this time we only train the model on the real banknotes. So we're using the same data set as before. This time we only keep some of the fake banknotes just for evaluating the model's performance at the end. We're not going to use them to train the model. So this is really that kind of unseen data situation. The model's only going to learn what a real banknote looks like, not what a fake one looks like. So what we do is we build the generator, and this is a slightly more complicated network this time, although it's still not very complicated. We give it 512 bytes of noise. So this is just randomly generated data. And we have 2 hidden layers of 128 and 32 nodes. And its final output layer is the 4 data points that we've already seen in the data. So the generator takes noise and generates fake banknotes, if you like. The discriminator similarly takes the 4 inputs that we've already seen both from the generator and the real data. And again, we have a few more hidden layers this time, just because this model needs to be a bit more complex. But again, we have a single output, which represents, is this real or is this fake? And so what we do is we go through and define the training method. I won't go into this in detail, as there's probably a lot of terms that are over your head. But if you're interested in this kind of technology, I definitely recommend going in and just understanding what a few of these terms are. This is actually a relatively simple example, and even if it looks scary at the moment, once you get in and a bit more familiar with some of the terms, it's pretty straightforward. So going through, we just have the training method. And again, very similarly, I'll just have it print out, its accuracy every 10 epochs. The important thing to note here, and just to reinforce this point, is we're only training it on the real banknotes, not the fake ones. But when we come down here, we do actually test how it performs on the fake ones, just to make sure that it's going in the right direction. It never gets to see the fake banknotes during training, but by evaluating how it sees them afterwards, we can test that this model's working. So again, I'll just run that example for you. This one takes a little bit longer to run. As you can imagine, it's a slightly more complicated type of network. So we'll just give that a second. So you can see it's running a bit more slowly. And it started off very inaccurate. We can see up there 6% accurate. So it's getting most of them wrong, even worse than a coin flip, which seems hard to believe. So I've just got this hard-coded to run through 600 training epochs, and that's just an arbitrary number. There's lots of different numbers we can tweak in this. But we can see it finished here getting about 76% accurate, which
was a bit more accurate before.
It was. You did well to see the previous results I had. One of the things with training neural networks is they start from a random state and they train from that random state. And if you imagine the number of parameters, in the neural network that I defined with, hundreds of nodes, there are going to be, thousands of parameters. So yeah, that's a valid issue with neural networks. But by tuning the parameters and maybe starting it from certain points, or even just trying it again and again, it's possible to turn, to get different, different models. So yeah, but yeah, 76, as you say, it was higher before. Just in experimenting with this model, I've seen it get up to about 93%. Which isn't far off the 98 that that we got in the naive case. So I think this is a really cool example of the the kinds of things that we can do with with machine learning. We've trained a model to recognize fake banknotes without ever actually having a fake banknote to show it. So this kind of unsupervised learning has real possibilities for us, in combination with what Nick's looking at. If we know that everything's kind of worked fine so far, we can potentially have, build warnings in or alarms without ever, having an error, which I think is really cool. Anyway, that's my demo. Does anyone have any specific questions?
I have a question.
Yeah.
Yes, I have a question about the first experiment. So was the data where you tested the accuracy the same data you trained it on?
Not intentionally. If there was a problem in the code, that could have been the case.
Good, because if you trained it on the same data that you tested it, it might just have learned the data.
No, exactly. Yeah. So no, you can see here I trained the model on this train features and train labels, and I tested it on the test features and the test labels. And yeah, they were separated out at the start.
Lovely.
Oscar, I've got a question if Henry's all done. So you mentioned that you use TensorFlow and using that library. So does that mean like what you're doing on a day-to-day basis is trying to figure out for a specific problem how to integrate that library to make the neural network, or are you ever like actually making the functions to like do the machine learning yourself? Are you just like trying to figure out how to integrate it, or are you actually building from the bottom up?
Yeah, no, that's a great question. I see TensorFlow as very much like a toolbox from which we build, models that work for our applications. So, in the same way a builder doesn't go and, make his hammer from first principles, we don't need to reinvent the wheel for TensorFlow that, does the actual tensor arithmetic internally. It just provides a really nice way to, you can see how simply we can build, a neural network. Neural networks are obviously a relatively new way of doing machine learning type problems. We still do older style things like, just linear regression. I didn't actually build a, linear regression model for this use case, but I imagine it would perform pretty well as well in this naive case. Obviously, there's no way to do that for the, for that more complex case.
Yep. No, thank you for that.
Oh, good. Does anyone else have any specific questions to this demo? Otherwise, I might just quickly share this. Can you all see that? So definitely keen for you guys to get involved. If, you're welcome to fork my repo that I just showed and, have a play around with it, try it out on different data sets. Try experimenting with the network yourself, just tune the numbers and see if you can get, better or worse performance. All the instructions are there. I'll have a go at what, Nick was looking at, get involved in AWS, sign up for a free account and just start playing around with the different services they offer. Because cloud is really the way that, all businesses are heading. If you're interested in joining our team, if you'd like what you've seen today, we have a lot of ESIPS placements going. I know the round just closed for those of you looking at doing it next year. But definitely apply when you want to do your thesis if you're interested. There's no experience required. We take across all the AMME and biomed streams. So definitely get involved. If you're looking for summer internships or grad roles, we recruit grads on a rolling basis, and we are still recruiting for this summer for interns. So if you're interested in that, just shoot us an email at the name and address there. But apart from that, happy to take any questions from anyone in the few minutes we have left. If we run out of time, maybe you guys, SUMO guys, you could collate them and email them through.
Yeah, we can definitely do that.
Cool. Does anyone have any questions right now?
Looks like we just had one in the chat. Steve wants to know, why are we seeing training differences and how would this training happen on different data?
So when you say training differences, you mean in like that final accuracy score or?
Yes.
Yeah, cool.
Yeah.
So the reason is, so this kind of comes back to what I was saying earlier. The neural networks, when we initialize them, just have random parameters in them. And so you can think of it, as if, we're like on a very hilly terrain and the training process takes us downhill. Depending on where we start, we could end up at completely different points on this, multidimensional plane. So it's a really interesting side to the machine learning field is how do we actually get the best model we can as quickly as possible, and there's a lot of different approaches to deal with that. Obviously, the example I gave here was very simple. We just initialize it and train it once, and we take whatever that final result is. But the process of trying to improve that is called hyperparameter tuning, or HPT. If you're interested in looking into that field, we've actually got a couple of ESIPS theses going on at the moment, looking at how we can improve that. I mean, the traditional approach is just to brute force it. And, you just start from, a million different points on a grid and see which one gives you the best result. But obviously that's computationally inefficient. Does that make sense? Awesome. Thanks for the question. Johnson, good to hear from you. Wondering where Gans are used. At the moment, we're not actually using Gans in our team, but needless to say, you can probably tell it's an area of interest for us, and it's something we're looking into. Kind of as Nick said as well, we're only really just building out this big monitoring functionality within our team. But yeah, we'll definitely be looking at where we can, use Gans to support that. I think that, kind of like the example I've shown here, the ability to, it almost behaves like a one-class classifier, where we only know what one thing looks like. Having models that can recognize abnormalities, no matter where they come from or what they look like, could be really powerful. But yeah, it's a field where we're still exploring. So if you're interested, yeah, definitely shoot us an email.
Cool. I just wanted to let everyone know it is 5 o'clock. So if anyone needs to leave now, we will send through the PEP doc, the survey now for you to fill out quickly. But if for people who want to stay with questions, feel free.
Cool. Thanks again for running today, guys.
Yeah.
It's been really
Yeah, thanks for having us.
I was actually also curious how, I know you guys run the ESIPS program, so you obviously put a lot of effort into new current research, but like how important would that be in your daily role? Like considering new, maybe machine learning, or that kind of current research that's going on in the field?
Yeah, no, it's super relevant. We try to integrate everything that comes out of, we're pretty relaxed when it comes to SIPS theses. But yeah, we certainly look to implement anything. We try to find good alignment between, areas that, the students are interested in and that we're interested in, and try to, yeah, integrate them, as I say. In terms of, yeah, how cutting edge is it? I guess that's really up to the SIPS student at the time. But yeah, I mean, it's always going to be new for us. So that's good.
Yeah. Cool.
I've actually probably got a drop. Nick, are you okay to stay around for a little while answering questions, or do you need to run as well?
I can stay on for another 5 or so. Yeah.
Yeah, cool. Thanks, guys. Thanks again. And yeah, if there are any questions that you have specifically for me, feel free to fling them through.
Yeah, thank you very much.
That was
No worries.
awesome.
Thanks, Josh.
Yeah, and Nick, thanks.
Awesome.
No worries. Thanks, Josh. See you.
Sweet.
See ya.
See you, Oscar.
Hey, Nick, I just have one last question. So I know the two main technologies that you just showed us being with the AWS stuff and the machine learning. Are there any other notable technologies that you guys use like on a daily basis that, you guys need to wrap your head around that are pretty essential to your work?
Yeah, I suppose those probably are the two main areas. I guess in that sense, AWS is such a big item that really there's a lot of things in there. So really the data analytics is one side of things. But the whole idea of getting the data in there in the first place and making sure that process is not just reliable, but fault tolerant as well. We always say that things, it's not a matter of if, but rather when things go wrong. And you see that everywhere within technology and how software is built. So yeah, there's a lot of components there. I would say, yeah, within cloud, like I said, data ingestion is big. Also, a lot of using, I guess, serverless components. So again, a lot of work still involves standing up infrastructure and you know, clusters of servers in a traditional sense, but there's a big push to use things in a serverless way. So being able to say, you know, run my code or execute my functions without provisioning servers is quite a big push. And there's a lot of services now which allow you to build entire apps, you know, without actually having to worry about provisioning servers, which, you know, has huge cost implications. And also, you know, you can build things in, you know, 2 weeks now, which used to take 2 months or 2 years, you know, maybe 5 or so years ago. So it means you can do so much more now in such a smaller period of time. So I think, yeah, I would say the cloud and machine learning are probably the 2 things that can't stop my head. But I mean, there's so many components of the cloud that it's hard to narrow it down just to one aspect. And obviously there's different cloud providers as well. But I suppose it's like learning a programming language. Once you know basic concepts, maybe it's called something different or they have slight variations. But if you understand the concepts, yeah, you'll excel regardless of what the actual specifics are.
Yeah, fair, definitely. So it's just getting really good at a few niche things is pretty much what your team does with the services that you use. Rather than using a bunch, you just get really good at a niche topic.
Yeah, and I think yeah, I think naturally you will gain more experience and knowledge with things you use. So for example, there's services to manage databases, which we don't really touch because we use Elasticsearch service, which isn't technically under it, but we don't touch those relational database services as much because we never needed to, and because we can manage it without having to worry about provisioning those databases ourselves. But I would say, yeah, part of it is, yeah, you naturally gravitate towards more certain services depending on your work. And for us, that's resulted in some serverless Elasticsearch things, as well as data analytics. I think, yeah, as I said, if you understand the core concepts of what you're trying to do, then I think, you know, that'll give you a good understanding, even towards understanding things you're not familiar with. So I guess a good example is when I was looking at this data analytics stuff, it's not really something that I fully was across, but I suppose, like with anything, if you can ask, well, why would I want to do this? What's the benefit to, you know, let's say using lake formation as we described, like why would I use that over just looking at my data directly? And the reason is because it gives you, you know, as an example, a way to automatically create these schemas and a way to automatically link these services together in a much easier way, and controlling access as well. And these are common pain points that people have when they manually set up their data lake. So I guess if you have an understanding of why you'd want to do things and what you'd like to make easier, then I suppose that makes learning any service easier, if you understand, you know, what the end benefit is. And if that means, you know, your customers can get more out of your product, then that's a good thing as well.
Yeah, okay, 100%. Thank you so much.
No worries.